Okay, our last subtopic in this chapter, it is on conservation of angular momentum. So in this subtopic, you have to be able to explain and use angular momentum, and lastly state and use principle of conservation of angular momentum. So angular momentum symbol dia adalah L. So it is defined as the product of the angular velocity of a body and its moment of inertia about the rotation axis. So the formula is L equal to I omega, where L is the angular momentum, I is the moment of inertia, and omega is the angular velocity. So the SI unit is kilogram meter square per second. It is a vector quantity. We also need to understand about conservation of angular momentum. So it states that the total angular momentum of a system will remain constant if the net external torque acting on it is zero. That is, if the system is isolated. So because of the magnitude of the system is equal to L equal to I omega, we can express the principle of conservation of angular momentum jadi macam ni. Okay? So conservation of angular momentum requires that the product of I and omega must remain constant. So any changes in the moment of inertia requires a change in the angular velocity. Okay? Right, so for example, we have a girl spinning a skater doing spin on ice. So this is illustrating the conservation of angular momentum. So if her arms is outstretched, the moment of inertia is large, so the omega is small. So that's why when they want to spin faster, they would pull her arm towards her body so that the moment of inertia is smaller, hence she would spin faster. Okay. This one juga, as the student walks towards the center of the rotating platform, the moment of inertia of the system decreases because the angular velocity and not because the moment of inertia of the system decreases, so the angular velocity of the system increases due to the angular momentum of the system that remain constant. Next, for a diver, at the beginning of dive, she would pull her arm closer to reduce the moment of inertia. So when they reduce the moment of inertia, the angular velocity would increase, hence she can make more rotation. End of the dive, she would increase her moment of inertia by opening up her arms, and the omega would increase, slowing the rotation rate equal to less water splash. Okay, macam itulah cara dorang buat supaya si gini lah kali si pandalila buat supaya dia ada water splash. Macam tu. Okay? Alright, so that is the theory part for our subtopic number 4. Example number 4, a 25 kilogram child with an initial speed of 2.5 meter per second along the path tangent to the rim of a merry-go-round with a radius of 2 meter. The sentence doesn't seem right. I can't read it. Okay, good job. Initial speed along the path. Maybe we need to add run, kan? A 25 kilogram child run with an initial speed of 2.5 meters per second along the path tangent to the rim of a merry-go-round with a radius of 2 and jumps on. Logic sikit kalau dah run. So the merry-go-round, which is initially at rest, has a moment of inertia of 500 kilogram meter square. So initially, the speed of the child is 2.5 meter per second. Mass of the child is 25 kilogram. And then we have the initial speed of the merry-go-round as well, which is equal to 0. And given is the merry-go-round punya moment of inertia, which is 500 kilogram meter square. So we have to find the final angular velocity when the child is already on the merry-go-round. Okay, so for this type of question, we need to apply the conservation of angular momentum, where angular momentum is equal to mRV ataupun saya tidak tambah kat di sini. I need to add something. You need to know that it is equal to L is equal to mR v, oh tambah di sini je lah kan nanti. And then since v is equal to r omega, we can substitute in terms of omega. Okay, ini pun formula dia juga. Sudah ada. Okay, itu je. Nanti I'll add that into your notes lah. Okay, I guess you have to download back the notes sebab saya sudah upload tadi. Okay, so we have the formula L equal to mRV dengan L equal to mr square omega. So for this case, we know that it is also equal to I omega. So for the initial angular momentum, we are going to use the formula mRV because we only need to consider for the child. Since the merry-go-round pun equal to 0 juga the speed. So this is going to be mass of the child times the radius times the initial speed of the child. So this is equal to the moment of inertia of the merry-go-round plus with the child, and then r square sebab kita akan guna omega di luar. Omega f. Okay, macam tu. So kenapa ni tiada r, sebab the moment of inertia is already given, which is this one, and then this one is mcr square is for this part of the equation, and then omega dia tu di sini, similar to macam di sini lah, omega dia di tepi sini. Okay, so I hope you don't get confused by that, but if you do, there is no problem. I can always explain it back in class nanti. Okay, so this is going to be 25 to 2.5 equal to 500 plus 25 to square. And then this is the final angular velocity. Just rearrange that and you will get 0.21 radian per second as your answer. Okay, so yeah, that is how you are gonna solve questions that are gonna ask you about angular velocity gitulah. Okay, so usually you need to apply conservation of angular momentum. Alright, so that is on subtopic 6.4 in example 4.